Artificial intelligence surrounds our daily lives. It's quickly progressed from a concept to theory to applications. In a way, it can be viewed not as artificial intelligence, but as applied intelligence. My views were reflected in a presentation I made at Central Asian University this April. I titled it Applied Intelligence: AI-based design, fabrication, integration, and control of robotic systems. My background combines that of being an academic with a practitioner. In partnership with many others, I've worked to advance the interests, the inspiration in pursuing science, technology, and engineering opportunities and careers for students around the world. And not just by designing robots to play competitive games, but also giving them the tools to apply their innovations to solve real-world problems, such as this group from the Republic of Korea who designed a submersible to improve kelp farming. Is the future upon us when it comes to robotics? This spring, at the start of the new year, China showcased its proficiency in the field of entertainment robots. Robots that could dance, robots that could perform, robots that could entertain, much in the ways that humans have. And these robots applied their algorithms not just to the expected world, but to the unexpected world, when the friction wasn't quite the same as what they thought it would be. The robot performed flawlessly. Is the future upon us? The Lego Corporation in 1998 took a microprocessor and surrounded it with actuators, surrounded it with sensors, and created a system to engage students, to engage youth in this field of robotics. This year, January 2026, they moved from that robotics system to use the computer itself as a processor, to use the camera as an input device, and then to wirelessly send the signals as the computer would track human motions, and the signals would duplicate those actions with a Lego version of a human. In essence, a tool to teach both AI and computer science. We can explore the question of, is the future upon us, by looking at another question. Was the future upon us? In 2005, DARPA issued the Grand Challenge, a race across 100 kilometers in the desert. That race was won by the autonomous vehicle created by Stanford University, led by Sebastian Thrun. That team integrated a host of sensors and used a concept of machine learning to create the autonomous vehicle. Was the future upon us in 2005? Before we dig into the applications of AI tools for robotics, it's important to understand what is a robotic system and what are some of these AI tools that are being used to design, fabricate, integrate, and control robotic systems. So what is a robotic system? It can be something small that's used in our homes, such as the Roomba. It can be something a little more sophisticated, taking data from a variety of sensors to drive a vehicle autonomously.
The second tower catch.
It can also be something quite large, quite sophisticated, where the computer processes data from the spacecraft itself and interacts with actuators to recover that spacecraft as it returns to Earth. It also can be something quite as amazing as a tool to inspire youth about their future. But what is a robotic system? At its heart, it's a computer that takes data from sensors, computes that data, and creates actuator actions to control the overall system. In yesterday and before, the design, fabrication, integration, and coding was all done by the mind and incorporated, in essence, by hand. But as we move forward, increasingly AI tools are used in all phases of this process. They're used in the overall design of the robot. They're used in the fabrication of the components. They're used in the integration of the sensors with the actuators. And they're used in the coding of the entire system. A review of some of the AI models is important to understand how they are actually applied in the field of robotics. We begin with the basics, the large language models, the large multimodal models. In this case, a great amount of data is received by the tool, and it acts as a predictor of what comes next. Machine learning is an application where data is used and performance is improved without being explicitly programmed for every task. Statistics and optimization are used to get to the end result. If we take that machine learning and we use layers of neural networks, we have the concept of deep learning, where complex patterns are using vast amounts of data to make predictions about the system. The concept of a pet and its owner, with the pet fetching a stick. An action that has a reward, or it has a correction, it has observations. This concept of learning and reinforcing the learning that is desirable is in essence the fundamental component of reinforced learning, where actions are determined through a series of trial and error. Computer vision is one of the most important elements of applied intelligence when it comes to robotics, and this allows the machine to interpret and understand visual data. When computer vision is combined with LiDAR, with force sensors, proximity sensors, other sensors, you're able to create a single 3D understanding and representation of the world. Vision language models combine computer vision and natural language processing to simultaneously understand both images and text. One of my favorites, generative AI, in this case, an ant produced a winter scene on the left, and generative AI used its own context and learning patterns to create the summer scene of that same image on the right. All applications of optimization. Some view the concept of general artificial intelligence as the holy grail. In essence, AI that can understand, learn, apply knowledge across any intellectual task at the same level of a human. Within the field of robotics, AI tools are increasingly used in the world of control. The graph on the right from this paper represents the growth from 2020 to 2025 of AI-based tools. Leading the way are LLMs, VLMs, and diffusion models that are becoming standard practice in programming of robotics. And so we have the archetypes that lead to new utilities of the roboticist. Generative AI tools allow the roboticist to be a co-designer. LLMs and LMMs allow the roboticist to be a co-programmer, and reinforcement learning allows the roboticist to, in essence, become a behavioral designer. These tools have rapidly influenced the industry of robotics. And now we can dig in. We can look and see how AI-based applications are used in 4 different areas. We start with the concept of design. In this view, from prompting to production, the goal of design is to minimize the weight and space, maximize the strength, and design optimal structures and components. In the end, we have lighter robots, can carry a greater payload, batteries keep the robot running for a longer period of time, and there's a longer lifespan due to the reduced load on the robot itself. Along the way, there can also be a faster design build cycle. Traditionally, The system requirements were interpreted by a human who creates a computer-aided design model that was then revised and led to the final design, which was followed by prototype testing and other design iterations. As an AI component, the system requirements start the process. AI generative designs are created. They form candidate designs where simulation is then applied to allow the engineer to select the best choice and proceed to the final design stage. Autodesk was the first to take this concept of generative design in 2018 and use the system requirements to create a variety of models that then could be compared against each other and used as the basis for future designs. One application of this is the generative design of a standard seatbelt bracket. The device on the left, through generative design, had the number of parts reduced substantially, creating a lighter weight and a stronger single component. To do this, the Autodesk generative design process generates a host of designs within the software itself. It uses its own tools to evaluate their strength, their effectiveness, their overall weight, and proposes the best candidate to move forward in the actual production process. Autodesk Fusion 360 made this available to its customers in 2019, allowing the traditional block designs on the left to be optimized as the generative design on the right. Other companies have picked up the mantle of AI-based design. 2025 edition of SolidWorks automatically aligns and mates assemblies, automatically creates drawings. It has smart automation such as the alignment features and the features that create fillets based on what it expects the designer to want. Hand in hand with that is the AI-generated models, optimized assemblies, and renders using AI tools. One tool that popped out during 2026 is the software Meshi, which takes a two-dimensional sketch, a two-dimensional image, and adds the third dimension to it. What this results is a 3D model that can then go into production to create a 3D component from a 2D sketch. One company that uses AI tools in its design process is, in fact, NTOP. In this case, they use finite element analysis, computational flow dynamics within the design process itself to optimize the creation of end products.
Traditional advanced design forces you to choose between speed and fidelity when both are critical. NTOP changes everything. Explore hundreds of design variants with high-fidelity physics in the same time as it used to take for basic estimates. With implicit modeling, you can create robust parametric models that never break, so you can quickly generate any possible configuration of your design. And get near real-time performance calculations that enable deep trade space exploration and generate high-quality performance data at a pace aligned with project timelines. Arrive at design reviews with comprehensive trade-off analysis instead of rough approximations.
One example of NTOP is in this creation of an end effector for an industrial robot. The original end effector is shown here, and the NTOP product here. NTOP uses optimization, minimizing the amount of material, and maximizing the strength of the resulting product. In this case, making those decisions within the computer itself before progressing to the final solution. Some of the standard AI tools can also be used as design tools, in this case using ChatGPT to create a CAD model of a cell phone case. ChatGPT offers two ways of doing this. One is a step-by-step instruction on the left, and the other is to create the computer code that the CAD model can run autonomously. Doing the step-by-step model, we have a case, and doing the generated computer code, we can also create that CAD model. Moving into the field of electronics, Quilter AI applies the concept of reinforced reinforcement learning. In this case, they use existing data to more efficiently design circuit boards. Here, the Quilter AI reduces the number of intersections compared to that of a human designer. The next step, the concept of fabrication. When it comes to fabrication, we're talking about accelerating production. The use of AI within computer-aided manufacturing for toolpaths, feeds, and machining strategies. Coordinating manufacturing through AI that's optimized for parts itself and processing, and in situ monitoring and corrections for additive manufacturing. Cloud NC, CAM Assist, is one company that does that. This company makes use of existing CAD programs such as Autodesk Fusion, Creo, and others, and in the end, integrates that with computer-aided manufacturing programs. What they do is generate machining strategies. They optimize the speeds and feeds for the machining itself. And they do in situ monitoring for checking the part for its own quality and machinability. Extending that concept is Machinalabs, which in essence has two robots working together, one pushing against a material and the other resisting that push. What they're able to do is to use predictive modeling, AI-assisted closed-loop control, and create these shapes within the device itself, and then go ahead and cut them out. Divergent is a company that produces end-to-end design in digital manufacturing. Generative AI is the start of it, using performance criteria as the input for creating the actual component. Additive manufacturing is at the heart of that work, with real-time monitoring and correction of the printed parts, and then the automated assembly with laser-guided robotics and advanced adhesives to assemble the parts. What Divergent is able to do is take the traditional design with many components on the left and create this generative design, which is a number of smaller components that are then combined to create the overall assembly. Divergent technology starts with the system requirements and then applies computational fluid dynamics, finite element analysis to design the overall structure. When the engineer has the computer-aided design, it's entered into 3D printing, metal 3D printing, in fact, optimizing the use of a single bed to maximize the number of parts. Those parts are then cleaned and prepared, and then they are robotically assembled using advanced adhesives. From that concept comes a composite design that then can be tested and put into the field. When it comes to integration, what we're looking at is using AI agents to integrate specific components into an overall system, integrating the perception, the planning, and the control across a variety of robot subsystems. This reduces the time to implement and increases the system's overall effectiveness. The company FidLabs does exactly that. What they do is they automate the integration of sensors across a variety of systems. They use thousands of hardware components to help the AI agents, such as Claude Code and Cursor, understand the specific hardware stack and then auto-generate the sensor compatibility code. What we have then is the ability of taking a thermal imaging camera, a vision camera, a LiDAR system, and a standard robotic arm, and put them together so that they work effortlessly with each other, using AI to integrate these distinct systems. Recently, FidLabs was acquired by Nominal Systems, which is taking this design concept beyond the field of robotics. NVIDIA Isaac Sim is also an important integration tool. In this case, using actual data with virtual data to train robotic systems.
A major challenge for robot makers is the lack of large-scale, real, and synthetic data to train models. Human demonstrations aren't scalable, limited by the number of hours in a day. Developers can use NVIDIA Cosmos Physical AI World Foundation models to amplify data. Groot Dreams is a blueprint built on Cosmos for large-scale synthetic trajectory data generation, a reel-to-reel data workflow. First, developers fine-tune Cosmos with human demonstrations recorded by teleoperation of a single task in a single environment. Then, they prompt the model with an image and new instructions to generate dreams, or future world states. Cosmos is a generative model, so developers can prompt using new action words without having to capture new teleop data. Once a large number are generated, Cosmos reasons and evaluates the quality of each dream, selecting the best for training. But these dreams are still just pixels. Robots learn from actions. The Groot Dreams blueprint generates 3D action trajectories from the 2D dream videos. This is then used to train the robot model. Groot Dreams lets robots learn a huge variety of new actions with minimal manual captures, so a small team of human demonstrators can now do the work of thousands. Groot Dreams brings developers another step closer to solving the robot data challenge.
In this application, what is important is that what is created is actually the trajectory plan for the robot itself. In my world of competitive robotics that inspires students, that product was actually used with 4,000 real photos and 12,000 synthetic photos to train a robot to identify objects, in this case balls, and shoot them into a goal. One final example of integration is Jeff Bezos' Project Prometheus, originally announced in November of 2025, with developments since then. Project Prometheus is exploring the world of physical AI, AI applied to engineering and manufacturing. When it started, it quickly escalated into a $30 billion and now $100 billion fund to transform the worlds of engineering and manufacturing. And finally, the last element, that sense of control. In this case, the code tasks involve perception using the sensors and actions from the actuators with that computation provided by the computer itself. Large language model programming assistants are commonly used for generating traditional robot code. Also, general intelligence code, robots trained in the real world and then using that training for new challenges as they experience them. When it comes to AI-assisted control and application in robotics, the key is to create the actions based on the input. Typically, one programs a computer using historical coding, text-based with debugging tools. The common method now is to use a tool such as VS Code that's embedded with LLM-based inline coding suggestions, error correction for debugging, and auto-code generating tools. In fact, if VS Code is used with GitHub Copilot, we now have inline coding suggestions, inline edits, inline debugging tools, as well as a side agent that automatically is generating text-based robotics code. The user can in fact even select their preferred AI coding tool. With a group of Yale students, we developed a process using Gemini Gems, an AI assistant. The inputs to eventually code a robotics platform included the user's own background, the challenge that the robot had to achieve, the mechanics of the robot itself and its sensors, and an awareness of the environment that it would work in. What the GEM did was not only develop the code autonomously, but it did so in a tutorial fashion that walked the learning programmer developer through the process of how to create code to drive a robot. That was then applied around the world in a number of examples. Another tool developed by Gemini is Gemini 2.5, a robotics and embodied intelligence tool. In this case, we have vision, language, and action that are all integrated together. Robots of any shape and size can perceive, reason, and use tools not just for the environments that they were trained in, but for environments they have yet to be seen.
The demos at Google I/O were strikingly similar to demo videos that have been posted on Google's DeepMind YouTube channel for the past few months. In these videos, Aloha 2 robot arms have been shown autonomously packing a lunch.
Can you put the bananas in the clear container?
Including zipping up a plastic bag, folding a piece of paper into an origami fox, and slam dunking a mini basketball into a hoop, an action that Google DeepMind says the robot was not trained to do.
Can you put the highlighter away?
In this desk clearing example, the speaker doesn't specify where exactly items should be put away, leaving the robot to figure it out.
Please put the erasers away.
The robots seem to hesitate a moment before picking up the erasers that aren't in use.
Another case study comes from the company Physical Intelligence. The goal here is to produce the general purpose robots. They do it by building a neural network model to control any robot to do anything within the real world. To train that model, they have to create training platforms, but then also extend them through the use of AI prediction tools. In a very academic approach, this company also shares their data, in this case, a paper on the AI-assisted integration applications within robotics.
Physical Intelligence's vision is to make robots as adaptable as large language models like ChatGPT. But in the physical world, the key to Pi Zero's adaptability lies in its pre-training. Just like how ChatGPT and other large language models get pre-trained on vast amounts of text before being fine-tuned, Pi Zero gets pre-trained on diverse robotic actions. But instead of text, it's trained on everything from folding laundry to delicate manipulations like stacking eggs without breaking them. After this broad pre-training, Pi Zero can handle a range of tasks right out of the box. No additional training required for simpler jobs. And for more complex multi-step tasks, it can be fine-tuned, just like fine-tuning a language model. But here's where things get really interesting. To teach Pi Zero all these skills, Physical Intelligence didn't just gather robotic data from around the web. Since there isn't a massive database of robot actions like there is for text, they had to create their own data. They used a combination of vision language models that helped the AI understand both images and text, and then applied techniques from AI image generation like diffusion modeling to enable more generalized learning. This approach has allowed Pi Zero to learn faster from limited data, and it's making strides toward a future where robots could perform any chore we need. And Pi Zero's potential isn't limited to just homes. The technology could transform industrial settings too.
And thus we have our case studies. Case studies of generative design, AI-based CAD operations, AI-fused designs and analysis for the design of robotic systems. AI-optimized CAM, AI-fused design, analysis, fabrication, and assembly to create the components. The use of AI middleware and AI-integrated systems to create the functions that are needed. And finally, LLM and prediction models being used with vibe coding and ML-based control paths for creating robot actuations under the coding element. So we return to 2005, when clearly the future was upon us, and now can question, is the future upon us once again? Yes, it is. And the future of robotics will be and is accelerated by AI. My references are detailed below. Thanks for listening to this presentation on applied intelligence, AI-based design, fabrication, integration, and control of robotic systems.